how they originate from an expanded lightning channel. And I'm going to talk about the structure and illumination of ball lightning. Bead and ball lightning have been a mystery for 2,000 years or more. There are recordings long ago of people having seen them, although they're rarely seen. People see them once in a lifetime, usually. I have a friend who lived in Indonesia and he saw them many times. And I've personally seen bead lightning once. So I'll talk about what they are. Ball lightning is typically a luminous sphere. It's always associated with lightning. It's after a lightning strike. It's a 20 centimeter diameter luminous sphere of luminosity, something like a 60 watt incandescent light globe, and it stays glowing and floats about the place for 10 seconds. And nobody has been, until I wrote my papers, nobody's been able to explain how it works. Bead lightning is very similar, but that's where the entire channel breaks up into a set of balls and beads. And but I'll show that they're closely related. Here's a cartoon of what ball lightning might look like coming into somebody's house. And there are many reports. I mean, there's so many reports that in the last 200 years, there's been about 5 or 10 books written just on ball lightning. And you see that the ball is spherical, about the size of a soccer ball, can be tennis ball or even bigger. And in this case, it looks hairy. Here's an old woodcut of a fireball coming from a chimney. And I don't think that's fanciful. I think that's probably how it looks. And here's a picture from the British Bureau of Meteorology showing bead lightning. This is the lightning channel. And you see it's broken up into a whole lot of beads. I'll show you some more of that. So the main points I'm going to demonstrate is that ball and bead lightning originate from a lightning channel that's been expanded, then snipped into sections by a secondary discharge. And the illumination of ball and bead lightning is due to burning solid particles. So the problem with ball lightning is that most discharges in the laboratory or elsewhere are filamentary. In other words, they're narrow channels, and at atmospheric pressure, you never get a distributed plasma like ball lightning. So where does it come from? For example, I've seen experiments in Liverpool University and experiments at Culham Research Lab where they looked at fusion and such with arc currents of 20 to 50,000 amps. And from 5 meters away, you can feel the thump hit you in the chest, the shock wave from these things. But the shock wave does not produce an extended plasma. It's always narrow. And I don't think ball lightning's ever been produced convincingly in the laboratory. Bead lightning does occur with triggered lightning events. They're events where you have a cloud, a more or less pregnant lightning cloud ready to discharge, and they fire a rocket into the cloud with dragging a copper wire behind it. And the lightning starts, comes down, hits the rocket, and then goes straight down the wire. And in that case, you do get bead lightning, and I'll explain why. But, you know, although in the laboratory we don't produce distributed plasmas, this is at atmospheric pressure, mind you, not the low pressure discharge where you fill a glass tube with a discharge. No, this is at atmospheric pressure in air. And but lightning discharges can be quite wide. And I want to demonstrate that to you and explain how that happens. And we need to understand that in order to understand how we end up with ball lightning. Now here's some lightning channels. This is a photograph by Johnny Altery. I've been in touch with him quite a bit. And this is called the Sword of God. And you see there's a discharge channel coming down, hits this tree. And things to notice about it are that it's about the same diameter all the way up. Now, if we want to know how wide that channel is, here's a convenient telegraph pole. Now, in America, telegraph poles are about 12 meters tall. So we use that as a scale, and we can judge that that channel is about 1.4 meters diameter. I actually communicated with Johnny Altery, and he's sure that the film is not overexposed. That is really the diameter of the channel. And if you're not convinced by that, here's a photograph by the one on the right by Michel Krog in South Africa. And here's our standard telegraph pole, just sitting here. And judging from that, that channel is about 12 meters diameter. And the one behind is something similar. And on the photograph, there was one very similar over to the right. And note that these channels are the same diameter all the way along. That's important. Now, I developed a theory for the expansion of lightning channels, solving the continuity equation for electrons, positive ions, and negative ions simultaneously with Poisson's equation in cylindrical coordinates. Now, that's a mouthful probably for most of you, but I'm not going to trouble you with the equations. If you're interested in the equations and the mathematics, you can go to the papers I quote at the end. The calculations were made with three important assumptions. The first was that the current of the lightning channel is suddenly interrupted. Now, this does happen. I've got evidence of fighter planes hit with lightning, and the channel, that the current suddenly stops, changes. And this is due to a discharge somewhere else in the cloud that interrupts the current. The second assumption is that the lightning channel has a net positive charge. And this is because electrons have 100 times the mobility of positive ions, or negative ions for that matter. And in the discharge, the electrons are very hot and the channel is left positive. There's a lot of evidence for that. And what happens is that the channel in discharges, in laboratories and that, is kept narrow by the magnetic pinch effect. That's caused when a current flows through the gas and generates a magnetic field which clamps all the charges close to the center. That's why they're all filamentary. But once the current of the lightning channel stops, that magnetic pinch also stops. And there's a thing called space charge field due to all these positive charges. And once the magnetic pinch effect stops, then the channel just expands. And here's some calculations I made of this. We have electric field on the vertical axis and radius on the bottom axis. And the times here are, first of all, nanoseconds, then going to microseconds. Initially, the electric field is very high due to the space charge effect. And much higher than this field here, E star, where ionization equals attachment. Now, as the field is above that, you get rapid ionization. If it's below that, you get loss of electrons and the discharge dies. So while the field is above that, ionization occurs and the electric field moves out rapidly until it gets to about 1.5 meter radius in about 3 microseconds. That's very fast. And note that this will happen all the way along the channel. The current must be continuous from the cloud to the ground. If it stops, then it stops everywhere, and the same conditions apply. And so that's why the channel expands and is the same diameter all the way along. From the calculations, the ionizing wave activity and the ion neutralization can't produce the brilliant light output that you get from channels that we saw in figures 1A and B. So it was necessary to postulate a new theory where the expanded channel is illuminated by a secondary discharge. Proof of this postulate is in the next figure. Now, this is a photograph published in Nature by Matthias et al. And they estimate, this is a lightning strike, they estimate that the diameter of that channel is 1 to 5 meters. And it's brilliant. It's a lot brighter than normal lightning. And it's pinched. Note it's pinched there. That's because there's a current flowing axially along the channel. That's re-illuminating it. That was my theory about that. And the magnetic pinch effect starts to grab the channel and squeeze it in. But it's found in an ionized gas like that the squeezing is not uniform and you get pinching in different places. It's called the sausage instability in fusion research. And so that is a means by which the channel is chopped up into segments of bead lightning, and near the ground produces the spherical balls for ball lightning. Now, as I've said, the channel is 1 to 5 meters diameter, much brighter than the ordinary lightning channel. And this is caused by a large axial current, and the large axial current chops it into pieces. So that gives clear mechanism for the production of ball and bead lightning. Having produced balls, then it's necessary to try and understand how the ball lightning and bead lightning remains illuminated for the order of 10 seconds, when most sparks and discharges only last for microseconds. Once again, the continuity equation for ions and electrons was solved together with Poisson's equation, but this time in spherical coordinates. The beauty of that is that you can treat this, you can deal with a full three-dimensional picture of a sphere, but you don't have to do the other dimensions. You only have to deal with the radial dimension. That simplifies the mathematics and the calculations enormously. What happened is that the electrons form negative ions within a microsecond, and they play no further part. So then you're dealing with a plasma with a lot of positive and negative ions flying about. But we have excess positive ions. We assume that the excess positive ions of the channel remains an excess positive charge in the ball that's been snipped off. And the space charge field in the excess positive ions drives them from the center of the ball. Very simply, the positive ions don't want to be together. They drive each other apart. However, the same field that's driving the positive ions away from the center drives negative ions the other way. And so you end up, after about 100 microseconds, forming a plasma with zero electric field at the center of the ball. And that's basically the structure of ball lightning. It can last for 10 seconds. Here's some diagrams. The ion number densities on this axis, the radius on the bottom axis. The red curves are the positive ions, the blue, the negative ions. T equals 0, that's the start of the calculation. And you see there's the initial negative ion density. As the calculation proceeds, the positive ions move out away from the center, and the number density decreases in the center. But the negative ions move towards the center. And eventually, after 100 microseconds, their numbers are almost the same at the center. While this is going on, there's a lot of recombination going on there too. In other words, positive and the negative ions are neutralizing each other. So both number densities are going down. And here's the electric field. This is the initial field. And you see after 100 microseconds, you almost have zero field in the middle and a positive field outside, which is what's driving the positive ions. It's the repulsion of positive ions, forcing them away from each other. After 1 second, we have this distribution here. We have negative ions, blue, positive ions in the red, and they overlap completely. And there's a nice rounded edge there because I include diffusion in the calculation. After 2 seconds, it's come down here, 11 seconds down here, but the structure in the center stays the same. And outside here, there are no negative ions, just positive ions. And there's the only equation I'm going to trouble you with is this one, which is the number density of ions, either positive or negative, in the central region is given by, very simply, 1 over time times the ion neutralization coefficient. Very neat little equation, very handy. So now, if we look at this curve on the right, we see a very interesting thing, which I'll come to later. If we get solid particles inside that central region somehow, and they're ionized, in other words, you have positive and negative, they're charged. We have positive and negative charged particles, which are burning. The positive particles will rattle around here. When they get here, they'll be driven away like the positive charges. So they'll just leave. But the negative particles will go into this region. They'll be driven back like the negative ions. So this region here becomes a trap for burning negative solid particles. And I'll come to that in a minute. Once again, the ionization and the ion neutralization is not enough to account for the luminosity of ball lightning. The luminosity, it looks like a 60-watt globe floating around, and that's equivalent to about 1 watt of 1 watt of light power coming out. And there's been a direct observation of ball lightning. There were people, Chen and Co. in 2014 were looking at a discharge on a mountaintop about half a kilometre away with spectroscopes and everything to look at the properties of the lightning discharge. And they happened to see ball lightning, and they measured the spectrum of ball lightning, and they got the spectra of silicon, calcium, and iron. So that tells you something about what's going on there. Thus, in general, the illumination of ball and bead lightning is due to burning particles caught up in the ball. For ball lightning produced near the Earth, the fuel comes from the soil, and this counts for the range of colors that you get for ball lightning, depending on which elements are caught up in the ball. For triggered bead lightning, the fuel comes from the trigger wire. There'd be some copper or whatever the wire is made of, would be exploded and be burning inside the beads of bead lightning. For other instances, it maybe the one I saw was due to smoke particles providing the fuel. Now, there's various burning particle theories. A Russian guy, Smirnov, in 1976, just simply said that the energy liberated in ball lightning can only be maintained if the energy comes from, is chemical in nature. And I think he's quite right there. He's got nothing to do with vodka, I don't think. Now, from my friends in New Zealand, there's a guy called Abrahamson, another one called Dennis, had a theory of ball lightning to do with oxidation of silicon nanoparticles forming a network. It probably happens, but you need my structure to hold it together. Now, Chen, Yuan, and Zhu, they're the people that made the observations of the spectra of ball lightning. Now, to give you an idea, these are the range of colors reported for ball lightning. Remember that people see them once in a lifetime, but there's sufficient people have seen them to get a curve like this together. And you see it goes white, red, orange, yellow, green. The only way you can get that great variety of colors is by the chances of the elements that are caught up in the ball light, the ball lightning. And generally ball lightning gets the fuel from the soil. And so ball lightning is down near the soil, but bead lightning, here's bead lightning. This is another photo. This was taken from a US destroyer, which dropped a depth charge into the ocean. And you can see the water blown up into the air. And at the crucial time, lightning struck and it formed bead lightning. And they managed to capture it on film. You see the beads there. Now, the fuel for that, we don't know. It may have been the smoke. It was probably an old-fashioned destroyer making lots of smoke. I mean, if it was anything like this, there's a lot of smoke. If lightning struck that, I imagine there'd be a lot of carbon to fuel the bead lightning. Now, there may be some of you who are interested in producing ball lightning in the laboratory. Now, if the current from a capacitor bank, such as a Marx generator, was used to produce a filamentary discharge, and the current was suddenly stopped using a device such as a triggertron, then the conditions for producing an ionizing wave, which expands the channel radially, may be achieved. Now, this might have been done before. Such an extended plasma region would only be visible if some kind of fuel was added, like a trigger wire or soil particles dropped into the region. Otherwise, with no fuel, you produce phantom plasma balls. I was very, very pleased when I thought of that name in my first paper on ball lightning. So phantom plasma balls, and they may well have been produced in experiments, but they would have gone unseen because you only get light output for a millisecond. You don't get light output for 10 seconds from that kind of thing. Now, what else can this theory explain? Well, the different appearances of ball lightning surface due to the size of the burning particles. My friend who saw ball lightning in Indonesia said they were very smooth surfaced. Well, in that case, the burning negative particles that are trapped inside it were probably very small, very fine, and they're very light. They don't go very far into the field caused by the positive ions outside the ball before they're turned back again. Some ball lightnings described as hairy. Well, in that case, the particles would be bigger, and the heavier ones can go quite a long way away from the ball into that rising electric field due to the positive ions before they're driven back in again, giving a hairy appearance. People describe streamer-like streaks inside the ball and streamers leaving the ball. Well, streamers are a particular kind of electrical discharge, and you can only see them in a very dark room with dark adapted eyes. You can't see it in the daylight. And the streaks they would be seeing would be burning particles moving inside the ball, back and forth inside the ball. And the streamers outside would be positively charged particles escaping. And a good piece of evidence for all of this is that when ball lightning hits wooden surfaces, quite often it leaves a burn mark. Now, this burn mark would be due to the burning negative particles inside the ball. And finally, quite often it's reported that a dusty brown residue is left when ball lightning decays. And this is clearly evidence of the burning negative particles inside the ball. So these are the papers I've published on it. If you wanted to read them, I'd say start at number 5, then 1, 2, 3, 4. Number 5 is more or less a summary of this talk, and the rest are pretty technical, but all the equations you require are in there if you do require them, and the methods and references to ball lightning literature. So the only thing to say in conclusion is, goodness gracious, great balls of fire. Thank you.